Okay, so the session James going to be talking about is creating game engines surprisingly simple, and I am actually excited for this. James Morgan, he's going to be our speaker for this session. He's a full-stack senior consultant at Insight with a passion for all things game dev. Welcome, James, please.
Awesome, thank you everyone. So today I'll be talking about crafting your own game engine and how it's actually surprisingly simple. So first thing, just a bit about me. I'm a senior consultant at Insight. I'm also CEO of my own startup, Pot Pirate, which is a craypot theft prevention. And I'm also passionate about all things game dev. Firstly, I'd just like to thank all the sponsors of this event. Without you guys, it wouldn't be possible. And a big shout out to Microsoft for being the room sponsor. So we're going to cover a few things today. We're going to cover what is a game engine, some modern game engines, the architecture of the game engine, run you through the simplicity of an engine, using the facade pattern, practical tips for getting started, some pitfalls, best practices, and then a Q&A at the end. So what is a game engine? Well, the official definition on Wikipedia is a game engine, also known as a game framework, is a software development environment for people to build video games. This is a nice definition, but it's a bit confusing. I think it can be a lot simpler. A game engine is a set of reusable libraries that can be glued together to build a game. So what do I mean by this? This means that it could be as simple as just a bunch of reusable classes that you write, for example, a math library that you share throughout your games. So what are the roles of a game engine? Well, it serves a few key roles. The main one is platform abstraction. This means that it shouldn't be relying on being a Windows-specific, Mac-specific, Linux, mobile, or desktop. The other one is it should provide reusable libraries. This means that the libraries, such as your physics engine, rendering engines, or math library, should be reusable without tight coupling. It should also provide development tools. This is for the game developers and artists. They want to have an easy time developing the game, and they want to focus on the game itself and not the tools. So what are some modern game engines out there? Well, right now, one of the most popular ones and gaining traction is Godot. This one's super popular as it's open source, community-driven, versatile, and very lightweight, coming in at under 100 megabytes in size. So very easy to install and run. Another popular one is the Unity engine. Unity is very popular for small to medium-sized games, and it's widely used, again, quite versatile and has a robust toolset. This is more on the 10 to 20 gigabytes in size. Another is Unreal Engine. Now this is if you want AAA studio quality games. It has a robust toolset, it's closed source, and it's again widely used. This is mainly used by a lot of AAA studios such as EA. This is in the 50 to 100 gigabyte size. Going into proprietary engines, there's two that I can think of that are the most sort of out there. The first being Frostbite, and this is done by DICE EA. They use this for all their games such as FIFA and Battlefield. It's very high performant and focuses on realism. The other is Rage, Rockstar Advanced Game Engine. This is the one used for all GTA games and Red Dead Redemption games. This focuses on realistic worlds, AAA quality, and high-fidelity tooling. If you've ever seen any of the GTA games, you know they're quite open world and has a vast graphics engine. So what about a high-level overview of what an engine looks like? Well, this diagram here is by Jason Gregory, and it's the architecture of a game engine. This is a very confusing and very small diagram, and that is the point. It's meant to scare you and think that game engines are hard, but they're not. This is really what your core systems will look like. You'll have a sound engine, a math library, a physics engine, a rendering engine, and some sort of window management. Now, the core ones that you would need is your math, physics, rendering, and window, and sound is something that you'd want if you want a polished game, but maybe not necessary. On top of these core systems, you're going to want some sort of gameplay systems. So this would be your scene management and entity management. On top of that, you might want to add in scripting, an editor, terrain, AI agents, and multiplayer, for example. These are what I refer to as gameplay systems. So they're not the core to the engine itself, but they're nice to have to be able to build a game. So what about the simplicity of a game engine? You might be thinking, this is still quite a lot and it's confusing and that's not very simple. All those systems aren't very simple. Well, at the end of the day, a game engine is just a game loop. And what is a game loop? It's essentially just something that continuously runs while you're playing the game. For example, you might apply forces, resolve collisions, render, and then handle input. And it will just continuously do this until you exit the game. So what does this look like in code? Well, up here we have a very simple game engine loop, which will basically run a window and render some text on the screen until we're done. So we're going to jump into building a demo here, and what we're going to be building by the end of this is a very basic bouncing ball, which you can call the start of your first game engine. So moving into some code here, I'll just go to the next slide, is we're going to be drawing a canvas first. So this is your window. So you might be wondering, we want to build a ball, so how do we build that? Well, the first step of this is to have your begin draw, have your clear background, and then draw a circle. This draw circle takes in a position and a color and a radius. You might be wondering though, this still isn't really a bouncing ball. It's a red dot on a screen. So how do we get it to bounce? Well, to get it to bounce, we're going to introduce something called a ball struct. This will contain the position, velocity, radius, and color. And this will act sort of like our data for the game. In the code itself, once I transition to here, we're going to first set up a window, set the target FPS. We want to set the target FPS to 60 as using a really nice library called raylib. The frame depends on the physics, so if you set 240 FPS, all of a sudden your ball's going to fall really fast. We want it at a fixed sort of rate. The first thing is we set an initial velocity and position. So we set that to the center of the screen using a vector. Next, when we create the ball, the first thing we want to do is first apply forces to that ball. And this is where we increase the velocity by a vector constant. We then begin drawing and draw the ball. And this looks something like the following. We start the ball and it will just fall to the floor. So, it's still not bouncing, right? Like it's a ball, but it's not bouncing. So how do we get this bouncing? Well, for this, we're going to introduce some very simple collision detection and resolution. In this code here, essentially all we do is after we've applied the position to the x and y, on line 36, you'll see that we check the ball's position. If it is greater than the screen width on either side, then we invert and reduce the velocity by 40%. And then if it's on the top or bottom, which is this line here on 50, we will reduce it by 10% for the top and bottom. The reason for this is we just want it so it hits the sides, it'll reduce velocity faster, and will come to a stop sooner. So what does this look like? Well, now we have our bouncing ball. And you might be thinking, well, this isn't really a game engine. You've just drawn a bouncing ball on a screen. And this is where we get to refactoring time. We can refactor this to look more like a game engine doing the following. We'll create a few methods such as create ball, draw ball, update ball, and check ball collision. Now, in our code, when we go here, you'll see a pattern starting to emerge. The first thing we do is we want to apply forces to a ball. The next is we want to check collisions on the screen edges. And then we draw a ball. So this is starting to look more like a pattern that you could reuse to draw more than just one ball. This leads me on to engine schedules. So what are engine schedules? These are the schedules in which your game executes. The first being your pre-initialization, then your initialization, post-init, your game loop, and then your exit. The ones I want to focus on are the ones in your game loop. This would be pre-update, tick, update, and post-update. Now, pre-update is something that you want to happen at the start of every frame. This would be updating your delta time, clearing your renderer, and doing some basic scene management. The next would be tick. Tick is where you want to put all your game logic, physics, and AI and state updates. The reason for this is tick does not run every single frame. Tick will run at a fixed time step. For example, 60 Hertz. This means it'll run at 60 frames per second. It must be independent from your window and renderer, and this is so that your physics engine code isn't using all your CPU cycles. The same goes for game logic. If you have your game logic running every single frame, you're going to constantly get frame lag, and it's not going to be fun to play again. The next is update. This is something that has to happen every single frame, and if it doesn't, then you're going to get flickering. This is where you would do rendering, handling input, and do camera and GUI. Now, rendering, if you don't do every single frame, it's going to flicker, and input handling is an interesting one. You may or may not know that when you press a key press, if you don't handle it in that update frame, then it will be ignored. For example, if I did my input handling in the tick and I pressed a key and it happened between my two ticks, then it wouldn't be registered. And this is just how the event system on your computer works. The last is post-update. So this is something that has to happen at the end of your update frame. The most common for this is doing your window update, so swapping the frame buffers around, and doing some sort of render post-update and cleanup of your entities. The most common approach of this is implemented in OOP. This is where you would have an iSystem interface with all of the methods for each schedule. This is a super common approach, easy to implement, and quite robust. The other is the functional programming approach. Now, this is where you have your schedules as an enum. You have a function that you pass in that takes the engine as a reference into the parameters, and then you have your engine itself. The way this works is you would have an add system function on the engine, and this would take in the schedule and the method. The reason it has to have the engine as a reference is that because it is a functional approach, it doesn't have any sort of dependency injection or idea of what a class is. So how do we implement this? We're going to implement schedules using OOP. In our code, we have the iSystem. Now, the iSystem has a few things in here. It has the pre-init, init, post-init, pre-update, tick, update, post-update, and exit. And this is in C++, so the syntax might look a little confusing if you're not used to it. Essentially, C++ doesn't have any interface like Java or C#, so you've got to implement it using abstract classes. Next up, we would implement a window system. Now, this window system is where we're going to handle all our code for the window using raylib. So this is where we initialize our window and set the target FPS in the pre-init. Now, we don't want to do anything in a init, post-init, or tick. So in pre-update, we're going to begin drawing and clear the background. And then at the very end of the update, we're going to draw the FPS and end drawing. And on exit, we're going to close the window. The other one is we're going to create a ball system. Now, this takes in the ball structure again and the gravity constant and creates a set of balls, which you can see on line 60 here. This is a vector of balls. In most languages, this would be an array list or a dynamic array, whatever you want to call it. In C++, they call it vector. So we're initializing an array list of 60 balls, and then in initialization, we are creating each ball with the create ball method. Now, this create ball method is slightly different to before. It does contain logic for randomizing the position, velocity, radius, and color, and you'll get to see why in a second. The other is tick. So during our tick frame, we want to loop over each ball in the array, and then we want to call update ball. And this is the same as before in that it'll simply update the velocity and position of the ball. Now, once we've updated the ball's position and velocity, we then want to loop over each ball and check for ball collisions. It's important to note that you need to do this in a separate loop, as if you don't, your physics code won't be deterministic. In our check ball collision, we do the same thing about checking the screen edges and reducing the velocity. We then also have code for checking between other balls, and I won't go into this code as it's not a physics demo, but it is available on GitHub if you want to go into it later. Then in the update, we do an update loop, again, looping over each ball and drawing the ball. So just looking at this tick, you might see why you wouldn't want to run this every single frame, because if you ran this every single frame, you've got two loops iterating over your entities, so to speak, and this would cause a lot of lag. So moving on to main, you'll see that now it looks a lot simpler. We now have a shared pointer to an iSystem for our window and ball system. For those not familiar with C++, this is essentially a reference to your interface, and it's using smart pointers. We then have our array list of systems, our window system and ball system. The order in which they are added shouldn't matter. However, if there is a specific order, for example, you might want to have a renderer at a specific order, then you can. Then all we do is we iterate over each system for each step. For example, we iterate over all the systems for pre-init, we iterate over all the systems for init, post-init, and so on. Then, once we enter the game loop, we run pre-update for all the systems again, tick for all the systems, update, and post-update. Now, this is a fundamental flaw of the OOP approach, is that you have to iterate over each system and call them even if those methods don't exist, whereas with the functional programming approach, you would only call the functions that are needed. And then on exit, we run that. So now I'm just going to run this demo here, and you'll see sort of what the output is. So we have balls bouncing on the screen. The physics resolution isn't the best, so there's quite a bit of jittering going on. But this example runs through, what your entities would be, in this case balls, and sort of how you would create your first steps towards an engine. One thing I'd like to highlight again, just in the ball section, is how these balls are wrapped up in a structure called ball. There is no update methods or any sort of methods on this structure. It is purely data, and this is sort of the data-oriented approach to game engines. And so moving on from that, again, that was just our bouncing balls, we'll move on to the entity component system. So an entity component system is the data-oriented design approach to building your entities in a game engine. So what is an ECS? Well, entities are just IDs. Entities don't store any data, they don't store any methods, they are just IDs and point to something. For example, your entity might be ID of 0 and that's all it stores. How do you store your entities though? Well, this is what you use an entity list for. So this would be an array or dynamic array of IDs. The most common approach is to store entities in the order in which they're inserted in the entity list, for example, 0, 1, 2, and 3. Then you have components. Now components, again, they're data-oriented by design and they only store data. This means that your rigid body and transform component don't have any methods attached to them, such as resolve collisions or check collisions. The example here is we have a transform component, which is used for your position, rotation, and scale, which stores a vector, quaternion, and another vector for scale. Then your rigid body would have a mass, center of mass, force, and so on, whatever data it would need for your rigid body. And these are stored in a contiguous array. So this is designed to reduce CPU cache misses. Essentially, each component is stored in a bucket, for example, a rigid body bucket or a transform bucket. And anytime you want to iterate over these components, you grab the whole bucket and it's stored in your CPU cache. This means that if I want to iterate over my entities with rigid bodies, I don't have to search in the RAM every single time I want to grab a rigid body, as it's all stored there in the CPU cache once you grab that first rigid body. So reiterating, entities just point to components. They are just an ID. For example, you might have an entity that points to a transform, model, and rigid body, or one that just points to a transform and script, for example. Your systems don't actually care about entities. The systems actually just transform the data. So for example, your physics system would only take the data from the transform bucket and the rigid body bucket and then transform the physics engine based on that. As well, your rendering system would take the model data from the models bucket and the transform data from the transform bucket and draw your models where the position is. And then you might have some, such as a script system, that just takes one component list and iterates over those. So your script would then just iterate over the scripts and nothing else. And this is what it looks like all put together. Your entities point to data and systems transform that data. So building a monolithic game engine, what does it actually take to build? Well, unfortunately, you are going to need all of those core systems, and especially a sound engine if you want a polished game. So you're going to want a math library of some sort that is shared between your physics, rendering, and window, and then you're going to want a physics engine for realistic physics, a rendering engine to render to the screen, and some sort of window management. You're also going to want some gameplay systems. Now, if you don't have these gameplay systems, such as a scene management or ECS, then it's going to be pretty hard to build a game. Some really nice ones to have as well would obviously be an editor that makes your engine feel feature complete. You want some debug tools, you might want AR agents in there, and you're probably going to want maybe some sort of scripting language so people don't have to use C++ to make their game. This is where the facade pattern comes in. The use of the facade pattern allows you to hide all of your implementations behind a class and use a third-party library. For example, instead of building your own physics engine, create the API for it and then use a third-party library such as React Physics 3D under the hood. This means that at any time you can swap out the API with your own implementation or swap it out with another third-party library. The same would go for your entity list and entities using a library such as Ent. What are these sort of libraries that you can use? Well, the first would be a window manager. So a window manager is something that you would want to use, such as GLFW, SDL, SFL, or Win32 API. Now, the most common of these would be something like GLFW or SDL. A lot of games use SDL if they're using DirectX on the Windows platform, or you can go down the approach of using the Win32 API if you want Windows specific. Obviously, the downside being it would only work on Windows, so my recommendation would be something like GLFW or SDL. The other you want is a graphics engine. Now, the choice of your graphics engine here doesn't really matter too much as long as it's depending on the systems you want. The most common approach is to use something like OpenGL or DirectX. Vulkan and Metal are a bit more advanced, and Metal would be specific to Apple. First, diving into OpenGL, there are two versions. There is Legacy and there is Modern. Legacy is OpenGL version 1 and 2, and Modern is 3+. You'd want to use Legacy if you want the fixed pipeline, so not having to do your own shaders, and you're just running some sort of basic physics graphics engine, sorry. The most common approach would be to use a modern sort of OpenGL version, such as 3 or 4. The reason for this is you get access to being able to create your own shaders. The other choice, which a lot of game engines use, is DirectX, and this is because it's built and supported directly by Microsoft for Windows. Limitation being it's only on Windows. DirectX has two sort of major versions at the moment, DirectX 11 and 12. DirectX 11 is more like modern OpenGL, and DirectX 12 is a bit more like Vulkan, so it's a bit more low level. Another popular choice, which is somewhere you want to start once you've got a bit more of an understanding of game engines and graphics engines specifically, is Vulkan. Now, if OpenGL is C, Vulkan is assembly. It is that sort of hard. You've got to manage your own memory yourself in Vulkan and kind of do everything yourself. It takes over 1,000 lines of C++ code to draw a triangle in Vulkan, for reference. So yeah, DirectX 12 would be more like Vulkan, having to write those 1,000 lines of codes for your triangle, and DirectX 11 is more like OpenGL 4. Then you have Metal. Metal is what DirectX is to Apple. It is specifically for the Apple ecosystem, and it's what you want to use if you're developing for iOS or Mac specifically. My recommendation here would be to start with modern OpenGL, and then if you really want to get into the depths of graphics engines, jump into something like Vulkan. The next is your physics engines. Now, there's quite a lot of open source physics engines out there and a lot of proprietary ones, but we'll focus on some of the top open source ones. The new kid on the block is Jolt Physics. This was created by one of the creators of Horizon Forbidden West and is currently being implemented in Godot, for example. This is a great physics engine to start with, however, the documentation is a bit limited. Another really popular choice is Bullet Physics. Now, Bullet Physics is kind of not supported too much these days. It's moving into the Python sort of space for robotics. However, it is still a great library if you want a physics engine. The other is React Physics 3D. This is the one I've used the most. I do enjoy it. It does have its downsides like any, and this one, again, is sort of focused on modern C++ and is widely supported and has great docs. The other choice would be something like NVIDIA PhysX, which is supported by NVIDIA. Now, out of these, I would recommend either Jolt or React Physics 3D. With any of these, it's worth noting that when you're trying to implement these into your own engine, you don't want to couple them together with other systems. And it's worth keeping in mind the approach you're taking. If you are taking a data-oriented approach, you want to make sure that you're not breaking that design pattern when implementing these. So for entity management, you probably don't want to write your own ECS. It's a lot of work. It can be as simple as just arrays and using the indexes, or you could use GUIDs or something like that. However, a much simpler approach is to wrap it in something like ent or flex. Now, if you're interested in using modern C++ features and metaprogramming using templates, then you'd want to use ent. Ent is a great library. It's used in Minecraft, for example, on the Bedrock edition, and it's widely supported and used, and the docs are fantastic. The other option would be something like Flex. Flex is a C API, so if you prefer the C-style APIs over C++, you'd want to use Flex. My choice for this would be ent, mainly because it is widely supported in industry as well, has lots of funding behind it, and is a really nice library to use. So what are some practical tips for getting started then? If it wants to press, there we go. So when getting started, you want to start small and iterate. So you want to take the agile approach here. If you don't start small and iterate, you're quickly going to be swamped down with features that you want to implement, and you're never going to get anywhere. The other one is you want a modular design. So those systems that I implemented before, for example, the Windows and Ball systems, you want those systems to not depend on each other. So you don't want tight coupling between your systems, otherwise it's just going to become spaghetti code. Another thing to watch out for is scope creep. So everyone wants to create the next best sort of engine comparing to Unreal or something like that. It's just probably not the case. You don't have every day to work on this. It's not a full-time job. You do want to just focus on small little items. Don't be afraid to leverage third-party libraries. Use React Physics 3D, use Ent, and so on. You don't want to have to try implement these yourself to begin with. Make sure you read and learn. There's lots of resources online to read and learn, so constantly be reaching out and trying to find new resources to learn. The other recommendation would be diving into open source game engines. Now, for example, you might want to dive into the Godot source engine and see why the source code is messy, or how you could take inspiration from certain things. Not just Godot, but there's heaps of other engines out there. For example, Source Engine has been leaked on GitHub, so you could go and check that one out. And there's lots of other sort of open source engines as well. Most importantly, have fun. You don't want to have creating an engine be your second job. You want this to be something that you sit down on the weekend, write some code, make a cool engine, and have fun doing it. So what are some common pitfalls, and then how do we avoid them? Well, the most common pitfall is over-engineering. Everyone has been there in any sort of software development where you over-engineer your code. The other one is tight coupling between systems, like I've mentioned before. This is where all of your systems are too dependent on each other, and all of a sudden you don't have modular designs and reusable libraries. For example, I've seen code before that I've written where your physics code is directly coupled to the renderer. This means that if I wanted to change the renderer in the future, I would also have to change my physics code, and it's not good. And this is for debug purposes, so you might think, oh, I'm just going to add this in here and sprinkle this in here to help me debug my physics, and then you end up realizing that if you want to change this system, you have to change everything else. And that kind of leads me into sort of the poor architecture sort of designs there as well. And here are some resources, I guess, for learning. So the most common is Learn OpenGL, and this would be if you want to learn sort of your graphics APIs and learn how to create your own graphics engine. The other one is Game Engine Architecture by Jason Gregory. This is an amazing book on architecture itself in a game engine. And if you want to really dive into the depths of how AAA studios design their engines. The other is Physically Based Rendering book. This is more of an advanced sort of rendering techniques, so making your scenes look as realistic as possible. This book focuses on companies from Pixar and so on that have developed in-house render engines, and it's a great book if you do want to get down that sort of path. The other one is AAA studio research papers. Now, EA, Ubisoft, and all them Epic Games are always publishing research papers online about all the new techniques they're coming up with. For example, Nanite has a research paper on their cool rendering techniques in Unreal Engine 5. So yeah, definitely check out them. And then last of all, being YouTube. YouTube is a great learning resource, as we all know. And there's lots of YouTubers out there building their own engines that you could follow along with. So before I move on to questions, I do have a very quick demo that I was going to run through, if I can get it to work. But I think we'll move to questions first, and then I'll get it loaded. So yeah, any questions?
So, hey James, I have two questions. The first one is you talked about some advantages of the entity component system.
Yep.
And is there any advantages of OOP design over entity component system? This is my first question. My second question is, you talk about there are some downside with React Physics 3D library, but you didn't say what exactly are they. Maybe you can elaborate?
Yep. So I'll start with the ECS using OOP. Is that how you would implement using OOP, or?
Sorry, yeah, my question is there any advantages of OOP over ECS?
So your ECS would still be an OOP approach, so to speak. You'd still have an entity, class, or object. However, the underlying data structures would be data-oriented. Mm-hmm. So, for example, your entity would just be a class that wraps, an int or an ID of some sort, and it would have a nice method on it called getComponent. and the data itself is stored in a data-oriented way, so it's stored in those contiguous arrays. And what was your second question?
React Physics 3D, any downside?
So not specifically, I guess, with the engine, more so implementing it. So a lot of these third-party engines, such as React Physics 3D, implement their own ECS under the hood. So they're almost mini sort of engines, so to speak. So implementing them, you often have to call into their regions of memory. So they have an ECS, but anytime you call their rigid body, it exists in RAM, so it's not actually coupled next to your rigid body in memory. So the issue for that is you might be iterating over your rigid bodies. However, because it's using a pointer to their rigid body, it's actually still having to go out into RAM, and then all of a sudden you've got a CPU cache miss. So yeah, I hope that explains it.
Yeah, thanks.
No problem.
It's helpful.
Awesome. Any other questions?
This was more around the structure of systems. So you mentioned that the input handling should be done at the same time as rendering. If your systems that do game updates, etc., depend on the input handling, are there any like sort of ways you know that can like easily sort of handle that, like events? Like what have you found that works best for that?
Yeah, so the best way to do that would be events, and I did have it, but I didn't cover it, was you would essentially store the events for 2 or 3 frames after they're inputted, and this would mean that no matter what, even if you're calling game logic in the tick, you can still handle those events afterwards. So that's sort of how you do it, is you'd store those events in an array somewhere and have a read events with a generic sort of thing, and you'd store it for 2 to 3 frames. Awesome. Front.
Hey. Yeah, hey. The question I had was, are there like practical reasons why you would want to implement like your own game engine, or is it more just like for learning?
More so for learning. These days, most sort of studios will use Godot or Unity or Unreal. But it's more so just a fun thing on the side, but it is still applicable. So if you go and work at EA and you want to do engine work, you might work on their Frostbite engine, which is the one that they use for all their games. So there is still work out there for it. So it's more like learning, and then you could get a job in it if you want. So yeah. Awesome. Any other questions? No? Oh, yeah.
Hi, I do have one question. Is there any benefit in actually coupling some of your systems together, such as the rendering pipeline and your physics engine? I mean, yeah, you're saying that's a downside, but is there potentially any efficiencies that you could gain from that?
I guess there would be efficiencies because, all of a sudden it's not having to rely on third-party sort of interfaces or anything like that. But I would still iterate that the issue is then you wouldn't have a modular design. So if I want to reuse my physics engine somewhere else down the future in a different engine, or use it somewhere else entirely, all of a sudden I can't because I've got to bring my renderer with me. Obviously, again, there is upsides to it. You can sort of bypass having to do that middle layer and hide behind interfaces. But yeah, it's kind of performance versus, I guess, modularity. At the end of the day, if it's just for one sort of game engine, you might want to couple it a bit, but it's still probably not the best idea. But yeah. One more.
Hi, being a very avid online gamer, my questions are with first the rendering engine. Is it possible to do selective rendering, and which engine would be best at that? So imagine the situation where you have a camera viewport that is behind a wall, and you have to render what the character avatar could see, but not what's behind or obscured by the wall. So which engine would be good at that?
All sort of modern engines do that, and even OpenGL itself, for example, implements culling, so anything that's behind the camera viewport won't get rendered. There is, obviously, you want to make it so it's not maybe running physics in the background, so Unity and Unreal both and Godot all do that.
Right. It's just I've always not noticed that most of the games don't do it. They force the camera to zoom in.
Yeah, so they'll still implement culling, so anything that's not being rendered or on the screen won't be rendered. They might still be running game update. For example, if you have a player behind you, you still want it to, or an NPC behind you, you still want it to continue walking, but you might run that at a slower sort of tick rate or something. But yeah, both Unity and Unreal implement that.
Yeah, it's just from the player perspective, the forced zoom in is annoying as hell. It's like, can't they just selectively render the wall as transparent, maintaining the viewport distance? That's what I'm trying to get at. It's just one of the quirks. The other one with physics collision detection.
Yep.
What about when someone with a backpack sits on a chair versus someone that doesn't? Why is it that all the time the backpack goes through the chair?
That would be because the backpack doesn't usually have a collision collider on it. So usually you just put a capsule collider around the player itself, and any sort of third-party things like hair don't have colliders on them. So it just makes it so it's easier to, yeah. Less physics is good because then it's not going to be running as slowly. So, yeah. That's all good. Awesome, cool. Thank you for that. And yeah, thank you guys, and hope you have a lovely rest of DDD.